Hello, everyone, and welcome to the first lecture of Organic Chemistry 1, Chem 365, here at Bethel University. I am Alex Levins, and I'll be your professor for this course. Sadly, you can't see me, but I promise you that I will do my best to make this course as smooth sailing as possible. And so to do so, we're going to be going through the Mullins book somewhat, but we're going to be doing it in an order that is very easy to understand and hopefully will make life as easy as possible for everyone in the class while still providing you a good idea of what organic chemistry is and how to be an organic chemist. And so the first thing we have to talk about here in lecture one is Lewis structures and formal charge. But before we get to that, we kind of have to lay the groundwork for what is organic chemistry, right? Because the first thing that we got to look at is what organic compounds even are, right? These are the things that make up this entire idea of organic chemistry. And quite frankly, the definition is very simple. Organic compounds are just compounds that contain carbon and hydrogen, right? It's very, very simple in that way. And now it sounds really boring because we just have these things that contain carbon and hydrogen, but those aren't the only atoms we're going to see here in OChem. Instead, we also have another few list of compounds, but our periodic table is rather short. You see, we'll also bring in things such as nitrogen, oxygen, sulfur, and even phosphorus. And we will define these throughout the course as what are called heteroatoms. Right? So anytime you hear me say the word heteroatom, I am referring to one of these atoms here. And at the same time, while we have these heteroatoms, we have a couple other atoms that come into play, and these are our halogens. So these would be the same ones that you would know from Gen Chem: fluorine, chlorine, bromine, and iodine. Right? So these, as I said, we'll refer to as halogens throughout this course. Now, these atoms are great. They can do a lot of things. And so with them comes a lot of orientations that we have to worry about. So here at the beginning of the course, we're going to be talking a lot about the concept of bonding, right? And what bonds actually mean. And so when we're thinking about bonding, we have a couple different types of bonds that we're looking at. So these types of bonds, one of them, or well, both of them you should be familiar with from general chemistry, but it's not going to come in contact as much here. And then the other one is the one we're going to see more often. So there are two types of bonding. The first one is we have ionic bonding, right? This is what you would be more familiar with from something like Gen Chem, right? In ionic bonding, we always have some sort of cation and some sort of anion. So you can think of something like sodium chloride, right? We have that positively charged sodium and that negatively charged chlorine, and that comes together to make this very, very simple salt of sodium chloride. And so these ions do not share electrons equally, right? You can think of it as the chlorine has most of the electrons, so this is unequal electron sharing, right? These bonds do come up somewhat in OChem, but the main one that we are worried about for organic chemistry is our second type of bonding, and that is covalent bonding. Right? Covalent bonding, very simply stated, is the opposite of what we see with ionic bonding. Where ionic bonding is unequal electron sharing, covalent bonding is equal electron sharing. So we can think of something like a carbon-hydrogen bond here. Right, we'll draw this out as a full structure so that I'm not missing anything. But this bond right here contains electrons, right? And there's actually two of them in there. If we were to draw them in, they'd be these nice two dots as shown here. And these electrons are shared equally amongst the two atoms that are bonded, right? So in this case, they are shared equally amongst the hydrogen and the carbon. And so these are the types of bonds that we are actually worried about when we're talking about organic chemistry. And so when we're looking at these covalent bonds, all of these atoms can share those covalent bonds. But the first thing that we need to actually think about is how many bonds can an atom have? Because this is going to be the basis of drawing what we call Lewis structures. And these Lewis structures are going to give us a strong foundation for how to draw organic compounds. So, as you can see right over here, I've already drawn in a little bit of information for you, right? This carbon right here, as we see, is shown with four bonds. And this hydrogen over here, as we can see, as shown, it only has one bond. And everything is happy in this scenario, right? And the reason for this is because of how these bonds actually form, and it has to do with being able to share electrons equally. So, if we're thinking about that, we actually have to think about something called the octet rule. And the octet rule practically states that everything wants to have 8 electrons in its valence shell, right? Everything really just loves having 8 electrons. Now, that being said, that's not necessarily true, so we'll put that everything in some nice quotation marks, right? Because not everything loves to have 8 electrons, but we'll see those exceptions in just a second. So, how do we get to having 8 electrons? Well, the first thing we have to know is how many electrons are in the outer shell of an atom itself. And so to get this, we actually have to look at a truncated periodic table. Right, so we can draw a little something out right here. This will be our very small periodic table, and we're actually going to just add in a couple columns, and we're not going to worry about absolutely every atom ever, because again, organic chemistry doesn't focus on a lot of the periodic table. Now, what it does focus on is going to be some of these very important atoms that we listed above, and a lot of them you'll notice are in the top rows of the periodic table. So we have things like hydrogen, we have even boron shows up occasionally, carbon, nitrogen, oxygen, fluorine. Here's neon for the sake of it. Now, the reason I've drawn in this truncated periodic table, and again, it's not perfect, is if we look at the columns, which I have numbered up here at the top, right? Each of these columns is actually directly related to how many electrons are in the valence shell of the atom that sits in that column, right? So if we divide these up, we see that hydrogen has 1 electron sitting in its valence shell, right? That is essentially what we're looking at since hydrogen is in the first column, right? This means that it will have, like I said, 1 electron in its valence shell. If we look at something like carbon, on the other hand, that we've been looking at beforehand, carbon has 4 electrons in its valence shell. So what does that mean? Well, if we look at this in terms of the atom itself, right, we can think of carbon chilling out, and it has, like we said, these 4 electrons just hanging. But like we said before, due to this octet rule, right, the thing that says everything loves having 8 electrons, carbon currently has 4, but it wants 8. So, how do we get it from having 4 to getting up to these 8 nice electrons? Well, that's where other atoms come in, right? Because every atom wants to give 1 electron to make a bond. So, if we take a look at good old hydrogen, like we see up there, hydrogen has 1, right? But unlike carbon, hydrogen does not want 8 electrons. Rather, hydrogen is one of the few exceptions that, due to just having s orbitals, it only wants 2. So, to give it 2, that means that it wants 1 electron. And it can get that from that carbon, right? We can take the 1 electron from each of them and we can bring them together to make a bond. And this is what we see up top, as we saw before with that carbon hydrogen bond, where, hey, if we put them side by side and we now have these 2 electrons that make a bond, we have made them a little closer to happiness, right? Because this carbon, all it would need then is four hydrogens that each contribute one electron to give it the eight electrons to fulfill the octet rule. So, that being said, this brings up some common bonding patterns, right? Because it's very clear from this picture that if carbon has four electrons and it wants four, that means it's going to make four bonds. If hydrogen has one, it wants one, that means it's going to make one bond. So we have these things called common bonding patterns in organic chemistry that actually just help us see, based on the valence electrons, how many bonds does that atom want to get to eight. So looking at these, right, these are going to be our common bonding patterns. We see that based on the atom and its valence, we will end up seeing some number of bonds. Right, so there's our valence electrons. Here is our number of bonds that they want. And we're going to actually take a look at hydrogen. We already talked about that. We already talked about carbon. We're also going to look at nitrogen, oxygen, and something like fluorine, which is a halogen. So if we think about the valence electrons for each of these, right, we can look back up at that truncated periodic table in a second. We've already defined carbon and hydrogen as having 1 and 4 respectively. Looking back up at this periodic table, we see nitrogen is up here in column 5, oxygen is up here in column 6, and fluorine is up here in column 7. So what that means is these guys have those valence electrons, right? Nitrogen has 5, oxygen has 6, fluorine has 7. And remember, if all of these want octets except for hydrogen, who only needs 2, right, that means that our total here should add up to being 8, right? So carbon wants 4 bonds because with those 4 valence electrons, that tells us that it has 8, and that is a good octet. Now, if we do the same idea for nitrogen, oxygen, fluorine, nitrogen wants to have 3 bonds, right? Because that 5 valence electrons means that we only need 3 more electrons to get us to 8. Oxygen, on the other hand, wants 2 bonds because it has 6 valence electrons. And that means fluorine only wants a single bond because that will give it that last electron since it already has 7. So, all of these are very happy, right? They add up to 8 if we give them that number of bonds. So you can imagine that something like nitrogen, right? Let's say that we were to give this the number of bonds that it wants to hydrogens, right? We can draw bonds as lines or as electrons at the moment, but we will be using mostly lines to help us see these. And remember, each of those lines as a bond contains 2 electrons. So looking at this, if we bond that nitrogen to each of these hydrogens, we see that nitrogen at the moment around it has 6 electrons shown because remember that each of these bonds is 2 electrons. That does mean that nitrogen, who wants 3 bonds and comes with 5 valence electrons, will have 2 electrons chilling out as a lone pair, right? And these lone pairs make up for some of those bonds not being there. And it's because the atom specifically already comes with more electrons than what it needs. Because if you think about nitrogen as a free atom, we would be seeing something along the lines of having 5 valence electrons. And so hopefully that helps you see that these 2 electrons up here have to become the lone pair because we cannot have more bonds than this, right? If we had more bonds, we would end up having an overfilled octet. So we're going to use this idea to actually draw these things called Lewis structures. So let us look at an example of a Lewis structure. So we've already actually been looking at these as I've drawn all of these other things here. But essentially, the way a Lewis structure works is every atom is going to be drawn out with bonds between the appropriate atoms and lone pair electrons shown. So if we take a look up here at this NH3 that we have drawn, you can see that everything is drawn out. We have our nitrogen, our hydrogens, all the bonds in between, and the lone pair electrons. So with that being said, we're going to move on to something slightly more complicated. And we're going to take a look at something like this molecular formula here, C2H6O. Now, if we're looking at a molecular formula and we want to make this into a structure, we actually have multiple options. And we'll take a look at those in just a second. But the first thing that we want to do is we actually want to find out how many total valence electrons are present, because that's going to help us draw and make sure that we're not drawing things that don't exist. So to figure this out, what we're going to do is we're going to first take a look at all the different atoms that are here, right? We have carbon, we have hydrogen, and we have oxygen present in this specific structure. Now, we're going to then take that and find out how many valence electrons are in each of them. We've already discussed carbon has four, hydrogen, of course, has one, and then oxygen has six. We'll multiply that by the number of that atom that is there. And that's going to give us a total number of electrons for that atom. So for carbon, there are two of them here. So if we multiply that, like we said, we would get 8 electrons contributed from carbon. Hydrogen comes in. There are 6 hydrogens, and they each have one valence electron. We're going to end up seeing that there are 6 electrons from hydrogens. There is one oxygen at 6 electrons. That is going to also give us 6 electrons there. So if we add all those up and we just get a total electron count, we see that when we draw this structure, we should end up with 20 electrons shown in our entire structure, right? And so that is both within the bonds and the lone pairs within the structure. So let's actually try and draw a Lewis structure of this. Now, whenever we're drawing Lewis structures, I have some quick recommendations. The first one is that you always want to try to put the atom that can make the most bonds in the middle. So always try to put something like a carbon in the middle. Now, this won't always be perfect, but it's a good place to start. And then from there, what I always recommend is fulfill all of the bonds that you can and then move out, right? So fulfill bonds and branch out. So using this advice, let's take a look at how we'd actually draw this thing. Well, of course, considering this is C2H6O, the first thing that I would do is I would put down a carbon, right? And that carbon is going to be the center of where we start doing everything. Now, attached to that carbon is going to be 4 different bonds, right? And each of these bonds is going to take up electrons, which we'll count here in just a second. Now, this carbon, we can bond it to anything we want. But let's take some of these bigger atoms and also put them in there to see what they look like, right? So we can add in our other carbon. We can even add in our oxygen. And from these, we know that the carbon is going to have 4 bonds. And if we think about oxygen, remember that its valence has 6, so it needs 2 bonds to fulfill that 8. So it's going to have another bond right there. And now we'll notice that there are 6 different positions where we can put hydrogens now, right? So we can put a hydrogen here, 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 and then one bonded to that oxygen. Now, looking at this, we have to ask ourselves, how many electrons do we have shown in this picture? And remember that to answer that, we have to say that each of these bonds represents 2 electrons, right? There are 2 electrons in that bond. So if we count that up, we see we have 2, 4, 6, 8, 10, 12, 14, 16 electrons currently shown. Well, of course, that is not our 20, right? We are 4 electrons off. And so what we need to do now is we need to look and make sure that everything has an octet. So the carbons each have these 4 bonds around them, each 2 electrons. And so that means each one has 2, 4, 6, 8 electrons around it. So these guys are both good in terms of octets right now. If we think about all of our hydrogens, right, hydrogens only need two electrons, and they find that in the bond they have to carbon. So all the hydrogens are also good. But if we look at our oxygen, we notice that, oh, hey, oxygen only has four electrons shown right now. And that means that oxygen's not very happy. So those last four electrons that we didn't have present are actually lone pairs that we find on our oxygen. So now looking at this, we no longer just have 16. We have 20 electrons shown in our structure, which means that this is a valid Lewis structure for this molecule. Now, that being said, this is not the only valid structure, right? There are multiple structures that we can actually see that will be valid here. Think about it this way. What if instead of doing what we did there, where we connected both the carbons together, what if we took this same idea, but instead of putting both the carbons, we started with the oxygen in the middle? Now, like I said before, I recommend putting carbon in the middle to start, but again, that was just a good way to get us to find the first Lewis structure. Instead, here, let's say that each bond from the oxygen bound to a carbon, right? We can see here that, oh, hey, we can draw in all the bonds to these carbons and put in all of the hydrogens. And of course, we know from beforehand that our oxygen won't be happy unless we give it four electrons, so that it has a total of eight for its octet. And we see that, hey, this is also, if we count it up, C2H6O. And then if we do some quick counting, from our bonds, we have 2, 4, 6, 8, 10, 12, 14, 16 electrons. And then those lone pairs make up the last four. There are also 20 electrons here. So this is also a valid Lewis structure. Now, if that's the case, you may be saying to yourself, well, what's the difference between these? Well, clearly it's the position of the oxygen, right? In one case, the oxygen is in the middle, right? But in the other case, the oxygen is on the end. Now, this difference is actually, it has a name to it. So these are called constitutional isomers. And what this means is that they are the way they're constituted is a little different, right? Essentially, the definition of a constitutional isomer is as follows. They are the same molecular formula, right? So you notice that both of these were C2H6O, but they have different connectivity, right? So the way that these were connected are different. In one case, the oxygen's in the middle, in one case, the oxygen is on the end. So, with that being said, constitutional isomers are actually going to be very important for us because they're one form of how organic molecules differ, right? These constitutional isomers are not the same compound. They are isomers of one another. So, with that being said, um, there can be multiple constitutional isomers of the same compound, right? The more complex you get, the more isomers will be available. So we're actually going to start out by going on to another example, and we're going to take a look at a slightly different compound that's going to have a bit more of these isomers to it. So let's take a look at something that's just ever so slightly more difficult. C3H6O. Now you'll notice that all I did here was I added in another carbon. But if we use that same chart that we had used before, where we were looking at the atoms, the number of valence electrons, the number of atoms themselves, and then that total electron count, what we'll find is we still only have carbon, hydrogen, and oxygen. But the difference is all we did was add in an extra carbon. So that does change our electron total though, because now 4 by 3 is 12 electrons from carbons, 6 from the hydrogens, 6 from the oxygens, and this time we end up with a total of 24 electrons. So let's see what happens if we try and distribute these and make C3H6O. Well, let's do the thing that we said before, which is start in the middle with a carbon, work our way out. Let's say we did all the carbons bound together, and let's stick the oxygen on the end once again. So, looking at this, we can say, all right, each carbon wants to have four bonds. All right, the oxygen wants to have two. We can slot in our hydrogens. Remember, we only have six of them. So here's one, two, three, four, five, and six. And now we see we have a little bit of a problem, right? Because clearly we have not enough bonds for our hydrogens. So, seeing that, let's just say that, okay, maybe these bonds aren't here. Maybe instead we just have to have them, like we saw with the oxygen beforehand, as some lone pairs, right? But if you do that, you'll notice that, all right, now everything has an octet. Let's count up how many electrons are present. We see that there, from the bonds, there's 2, 4, 6, 8, 10, 12, 14, 16, 18 from bonds, right? So there's 18 electrons in bonds. And then if we look at lone pairs, there are suddenly eight from the lone pairs, which is confusing, right? Because if we add 18 and 8, we see that that's 26 electrons. So this is why we do this electron counting, because it's actually really important. Because we clearly haven't made a mistake in the formula, but the way we've distributed these electrons just aren't right, because we have two extra. So if we were to get rid of two extra, we would say, okay, fine. It's weird having lone pairs on a carbon. What does this look like? Well, now this is weird because this carbon right here is showing a missing octet. So the question becomes, how do we fix that missing octet while not messing up our electron count? And the answer is we can take this and we can actually make double bonds, right? All these single bonds are fine, but what we can do is to keep both the oxygen and the carbon happy, we can take one of these lone pairs of electrons and we can actually share it between the carbon and the oxygen by forming another bond there, right? Those two electrons can practically fulfill that carbon's shell. So if we were to redraw this Lewis structure in a more valid manner, we could draw something like this. And this is now a valid Lewis structure. So if you can't tell, Lewis structures do have to, unless a charge or something else is shown, they have to have all octets filled. And it also has to be the most neutral Lewis structure possible. So those are two rules that you got to follow, right? So if we're looking at rules of these Lewis structures, like I said, all octets have to be filled, and most neutral structure is best. Sometimes you cannot avoid having charges, and that's okay. However, we want to try and keep it neutral because that's going to be how the molecules want to exist. Now, here's my little challenge here that I want you all to undergo. I want you to try to draw two constitutional isomers of what we just drew, which was C3H6O. And you cannot use the one that we have drawn up here. I highly recommend taking the time to try and draw two constitutional isomers, not including that one. If you're able to do that, you're doing pretty good. So there's my recommendation here as we move on to the second part of this, which is formal charge. So formal charge is a different type of beast because, like I had said before, neutral is better. But charges can exist, just like we see in a lot of Gen Chem. Charges can be on anything. We can have either positive or negative charges. In organic chemistry, the definition is still the same, but we're going to use this really nice equation that'll help us determine the formal charge on any atom, and it'll help us do it very easily. So that equation is formal charge is equal to the number of valence electrons for the atom we are looking at, right? So this is that same number that we've been talking about the whole presentation, right? It is for carbon, it's always 4. It's just based on that column that it's in the periodic table. Now this is minus the number of bonds to that atom, right? So depending on how many bonds, you'll subtract that there. And then that is also minus the number of unshared electrons, right? So these can be in uh, lone pairs, is primarily the way you're going to see this. So looking at this, let's take a look back on why our carbon was neutral beforehand, right? So let's go back and let's look at the CH4 here. So if we're looking at the formal charge equation here, we can plug in some numbers. So the formal charge for our carbon, right, that's the one we're going to focus on, is equal to, like we talked about before, carbon has 4 valence electrons, minus the number of bonds. In this case, we see that carbon has 4 of them, and the carbon has 0 unshared electrons. So that means that the formal charge for this carbon is 4 minus 0. That is 0. And anytime you see 0, just know that is exactly neutral. And neutral is usually pretty happy. Now, if we took something a little different, let's say we did NH4, right? So this would be where that nitrogen has 4 bonds. Let's see what the charge would look like here. So the formal charge would be equal to number of valence electrons, which for nitrogen is always 5. The number of bonds, here we see that there are 4 bonds to the nitrogen. And then there are no unpaired electrons on the nitrogen, right? It already has an octet here. So our formal charge in this case, 5 minus 4 is equal to 1. And now that 1 is a positive number, right? It is technically a positive 1. So when we're looking at our nitrogen here, that means that it will have a plus charge. Now, in organic chemistry, whenever we're drawing charges, I recommend you always put a circle around it, right? And that circle is going to help because it's going to allow you to more easily see when an atom is charged, right? So the circle just makes it easier to see. And that's especially true with something like a negative charge because negative charges kind of look like bonds. So I highly recommend putting these things in circles. Now let's do one more example before we move on. What would happen if we took that nitrogen and we only made it an NH2, right? In this case, for that nitrogen to have an octet, it's going to have 2 lone pairs. So now if we take this and we do the formal charge equation, we see that nitrogen has 5 valence electrons. It currently has 2 bonds to it. And then we see there are 4 total unpaired electrons on the nitrogen. So this time our formal charge is equal to 5 minus 2, which is 3, minus 4, which comes out to negative 1. And so this nitrogen is negatively charged, right? So very simply, based on how many bonds an atom has, you can actually determine what its formal charge is. And that is actually where we bring in a extended version of that common bonding patterns, and we look at it on what it looks like whenever we have charges. So this is our new common bonding pattern uh, sheet, which we'll just call it revisited, where now if we look at a specific atom, there are a couple forms that it can come in. So let's start by looking at carbon. Right? The neutral form of carbon, we keep talking about it. And it's the reason is because I want to get it in your brain. Right? If we take a look at it, like we said before, the formal charge is equal to a classic 4 for the valence electrons of carbon, 4 bonds, 0 unpaired electrons. That is a formal charge of 0. But if we wanted to make this a cation, which is a positive one charge. What we're going to have to do is we're going to have to look at how to actually do that. So with carbon, right, for something like nitrogen, we gave it an extra bond. But for something like carbon, that's not actually going to work for us because essentially, if you give it an extra bond, it's going to have 10 electrons. And we can't have that. We can't break the octet rule, right? But the octet rule somewhat works in a little bit of a different way because although you can't go above 8 electrons, you can technically go below. Highly recommended that you don't do it because it's very unstable, but a cation for carbon would have 3 bonds. Because if you think about it, our formal charge equation would be 4 minus what would be the next thing? It's bonds. There's only 3 of them. And if there's no unpaired electrons on that carbon, then our formal charge would be equal to +1. So like I said before, this isn't necessarily a good thing because there is no octet on this carbon. And that means it's going to be very unstable. This is a possibility. We will not see it for a while. So just keep in mind that it can happen, but keep it in the back of your mind for later in the course. Now, one that's more likely to be seen is the anion, which is the -1 charge for carbon. So if we're thinking about how this is going to be done, it's actually a carbon with 3 bonds and a lone pair. Now, this is not very common to see because, of course, carbon doesn't really love having electrons, which we'll talk a lot about later. But for the formal charge of this, it has 4 valence electrons, 3 bonds, and then 2 unpaired electrons, which gives us a formal charge of -1. Now, we can go through and do this for all the other atoms that we looked at before, but we're just going to quickly do it with nitrogen and oxygen. So nitrogen, like we talked about, likes to have 3 bonds because it has those 2 electrons there. We're not going to do the formal charge equation of that because we just did. Same thing with the cation and the anion of nitrogen. We already did the formal charge equation for these up top. I don't know why I gave this one hydrogens. That is not necessary considering the fact we're just showing these as bonds. Right, a nitrogen with 4 bonds is going to be positively charged. And then a nitrogen with 2 bonds and 2 lone pairs is going to be negatively charged. Oxygen, on the other hand, slightly different, right? It is happy with 2 bonds and 2 lone pairs because if we think about its formal charge, 6 valence electrons, 2 bonds, and 4 unpaired electrons gives us a formal charge of 0. Now, if we take that oxygen and give it another bond and take away that lone pair, quote unquote, it's going to have a positive charge because now our formal charge is 6 minus 3 minus 2, and that ends up being +1. Whereas the opposite is where we have an oxygen with 1 bond, 3 lone pairs, in which case this formal charge is 6 minus 1 bond. 6 unpaired electrons gives a formal charge of -1. Now you'll notice that there's a very common trend amongst these, right? For the most part, anytime you add a bond to something, right? So going from this neutral nitrogen to this positively charged nitrogen, all you're doing is adding a bond, right? That is what normally takes it from a neutral to a positive charge. Versus if you want to go to this with a negative charge, normally this is taking away a bond. Right? This is true for every single one of these, right? Except for the carbon cation, right? Because we cannot give it another bond. But looking at carbon neutral to carbon anion, you're taking away a bond. And then looking at our oxygen, we add a bond to get to the positive, we take away a bond to get to the negative. Now we have a couple final things before we close out, and those are just some exceptions to the octet rule. And the reason I want to bring these up now is because I don't want them to catch you off guard later. Right, the octet rule is going to apply to practically everything that we work with, except there are 2 or 3 atoms that are a little different. And the first one I want to point out is one that we actually won't see until a couple weeks from now, and that is our friend boron. Right? Boron is a little different from other elements because it actually shows up in the third column of the periodic table, which means boron has 3 valence electrons. And the weird thing about boron is since it has those three valence electrons, really it only wants to use each one to form one bond. So the neutral form of boron actually only has six electrons, right? So it's an exception to the octet rule. It's because that boron just likes having those three bonds, and then it just kind of likes having nothing else, right? And it's all because it has those three electrons to start. Now, that being said, that doesn't mean that boron can't take another bond. That just means that it's going to be the anion, right? That is when we actually have all eight electrons by boron. And so we can do some formal charge equations to prove that this is the case. Because if we look at the formal charge of this boron on the left here, the neutral, right? The formal charge, like I said, this has three valence electrons. It currently has three bonds, no unpaired electrons. That has a formal charge of 0. Versus the one over here, formal charge, three valence electrons, but four bonds, 0 unpaired, gives us a formal charge of -1. So, boron's an exception because it's happier with just six electrons. Keep that in mind for later. It's not that important right now. The more important one right now is actually sulfur, because this guy likes to break the octet rule in just about every single way. Because its neutral form can be one of three forms. It can have a happy octet, it can have 10 electrons in its octet, or it can have 12 electrons in its octet. So if we take a look at the first form, which is the 8 electron form, it's very simple. It's the exact same as oxygen. And that's because it's directly underneath oxygen in the periodic table. Right? So it's just happy with two lone pairs and two bonds. But the thing is, since sulfur is larger than oxygen, it can do other fun things. So it can have a 10 electron form, which here is a molecule that does have this 10 electron form of sulfur. It looks like this. So if you count it out, we're looking at what is uh, 8 from the bonds and then 2 from the lone pair. And so, oddly enough, this really does look like it breaks everything to do with the octet rule. But like I said, sulfur's a little weird. It's a little bigger. And it can actually do this little thing that we're going to talk about next class called resonance here. And what it can do is it can split some charges around to actually form what is the sulfur octet. Right now, by taking away that one bond and giving it to oxygen, the sulfur now has a positive charge, but it does have an octet. Right? There are only 8 electrons around it. And so that's a good thing. We like having the octet there. So it's not that sulfur necessarily breaks the octet rule, it just does it in a slightly different way. And the same is true about the 12 electron sulfur species as well. And we can see this in something like H2SO4. Right? When we're looking at H2SO4, sulfuric acid, it's a little bit bigger of a molecule, but it looks a little something like this. And if we're looking at that sulfur in the middle, we'll notice that there are 6 bonds around it. And if all 6 of those bonds are contributing electrons, that means that, hey, it has 12 electrons around it. But again, it's kind of playing tricks on you. Because if we take a look at this other sort of resonance that we had talked about just a second ago, it can actually take away a couple of those bonds, give the electrons up to those oxygens, and suddenly it only has 4 bonds around it, and it's looking a lot like it obeys the octet rule. However, if we draw it like this, the sulfur is a little less happy because it has a +2 charge, which you don't see very often. So even though this has an octet as shown, we don't draw it this way. Right, for both of these molecules, if we're thinking about them, this is how we traditionally draw it. And that's why whenever I'm talking about these, I'm saying sulfur kind of breaks the octet rule because of the way that we draw these. Either way, just so everyone knows, these are some exceptions to the rule. Now, with that being said, that's everything that we have to cover for today. All right, so just as a reminder, we went through how to draw Lewis structures, right, which is incredibly important And that is one of the main things that I'm going to have everyone start to focus on in the coming week, right? So that was the first thing that we did in this entire lesson. And the second one was how to calculate formal charge. So as long as you were able to take away those two things from this, I think that we did our job. So, with that being said, next time we will hop into what is resonance. And resonance will start off a lot of the backbone of the rest of organic chemistry. But everything is foundational, so keep in mind that you do need to be very strong on this stuff. But there will be practice problems posted over every topic we cover. That way, you're able to really get into it and figure out all of these important pieces of information. Thanks for listening in, and I will see you all in the next class.